Good morning, everyone, including I really want to say a good morning to all my teachers and my teachers who taught me. So I am really happy to see my teachers, including Professor Amuba. And I couldn't see others because my screen is too small. So whomever, even though I didn't call their name out, I really wanted to say. First of all, I wanted to thank all of you for uh, all the advice and all the things you taught in my previous classes. I am here because of all of you, and I really appreciate your help and your guidance. So, with this, I would like to introduce what I wanted to do here and what I wanted to say in today's discussion or meeting regarding this International Year of Quantum Science and Technology. Actually, Professor Nimai asked me to visit over there, but I'm in middle of semester and our mid-sem is running on, so I couldn't come there. And other thing is that I am an experimentalist. I'm just starting my lab, so I need lots of money to start my lab. I need to thank my funding agencies, including IIT Kanpur and National Quantum Mission, and I have ISER Pune. So today, first of all, I will summarize what we know about quantum technologies. And then in the end, I will give you an example of this quantum measurements and quantum sensor, which I was a part of the measurements where we do clock frequency measurements. And while in the discussion, we'll come to know like what is this clock frequencies and what we were doing. And so I would like to start my presentation with the outline. So this outline, we'll go through this outline. By the end of this, I'll tell you what are quantum technologies and what we can do in the field of my working like light atom interactions and metrology and sensor. And so if you ask me how these quantum technologies come or what is your views in the quantum technology, is that technologies, what we were trying is that we are trying to search better technologies. What is the meaning of better technologies? Technologies are already exist. We are using many of them, but these kind of technologies are, when you say better technologies, you don't need to know what is happening in that. You just, like, anybody can use it. Any layman who doesn't know how to read and write can use that kind of technologies and make their life comfortable. That kind of technology is called better technologies. And on top of that, it should be everywhere the same. Like, it shouldn't be different in Imphal, it shouldn't be different in any other part of the world. And so it has to be like everyone who lives in Imphal or in the North Pole of the Earth or in the United States of America should have access of this kind of technologies. So a good example I can think of this kind of technologies is the GPS navigations, which every one of us have in our mobile phone. Right now, everyone who has access to the smartphone can use these GPS navigations. And this GPS navigation is possible now because of the invention or discoveries of this atomic clock, cesium atomic clock, around 1955 in the National Physical Laboratory, London, by these two famous physicists called Louis Essen and Jack Berries, right? So when we were invoking our GPS signal, our phone is connected to at least nearest 4 satellite up in the sky, and they are calculating our position. That is why we are getting some numbers, some accuracies, but still there are some error in the calculations. So people are trying to make it better. How can you make it better? One thing is to make your clock better, the precision of the clock which your satellite is carrying. So whatever the calculations we are doing has based on the clock they carried in the satellite. Even our internet, our mobile phone, all this timing synchronization has done using this kind of technologies. Next thing is and if you say we are in the process of exploring other quantum technologies, for example, quantum internet. And when I said quantum internet, we will think that it will replace our classical existing internet. It is not like that. Quantum technologies will not replace the existing technologies what we have. It will just complement the technologies which are there. So it will complement the internet, but this will work in the it will work with the quantum processor, quantum channel, quantum carrier. Like that, another very good example I can think of is this quantum secure communication. We all use, I think every one of us use now secure communications because we need OTP, right? One time password for transaction of any bank account or any money in the banking system. So this is a kind of good example of this quantum secure communications. When the quantum secure now the present existing OTP generation is based on an encryption algorithm called RSA encryption, but that is in the verse of cracking, means it can like it will not work when our quantum internet, quantum technologies, quantum communications develop, because they can hack, a hacker can hack the communication, and because it doesn't base on this our quantum properties, like what are the quantum properties we will be using in quantum communication, like the collapse of the wave function, right? We prepare a state, and once we do a measurements, it lost all the properties. So even though a hacker wants to hack our information, he needs to do the measurements, he wants to read out the information. Once he tries to read out the information, that information will not be useful to us. So this is one good example of the quantum communication which we have to develop, and it's already shown in the some part of the world, like including China, that they can use these secure transactions in their banking system. And in all this quantum communication, internet or clock, they need quantum processor. So among the quantum processor, there's a is a huge fight, or I would say a competition among this quantum computer, which will act as a quantum processor. In recently, Willows has come up, like Microsoft is claiming that can use the topological insulator states, all this kind of states. But we are trying to find which one is the good quantum processor. But there is a catch here, is that one of them, like I cannot say an ion trap or a superconducting qubit. You can see the left side image is a superconducting qubit quantum processor, and the right side you can see a chip where we are going to trap the ion trap. So that will be a good quantum, like, because their superconducting qubit is good in doing calculations, but it has very short coherence time. What is the meaning of this short coherence time? We will explore when we go through the discussion, but it's very short-lived. You can think in this way. So we cannot do many many algorithms, because we have to perform many gate operations, which is like similar like the classical algorithm and classical gates, classical algorithm implementations. So but the ion trap has another advantage. It has a long life, so it can be used for other kind of applications. But ion trap cannot do faster computing. This is also one thing. So, and one of them will complement, like all of them complement each other. And this quantum processor needs to be connected using to make quantum internet. Let's say the quantum processor need to be connected. How we will connect? Either in a free space in the internet, or we will be using the optical cables, which was already used. Means the telephone network cable or the internet cable, optical cable lying in the ground in Imphal, that can be used for the quantum communications also. So what does it mean? The optical cables which are lying down underground are made for 1550 nanometer. The telecom wavelength where we used to communicate in the telephone or internet, they base on the wavelength of the light they use there is 1550 nanometer. So it is good for that particular wavelength. If I wanted to send another wavelength, let's say 780 nanometer, it doesn't propagate. I have to lose all the signal. So the signal loss is there. That's why we need amplifier and repeater. Okay, so that quantum repeater, that is another research field or another topic people explore while we were developing quantum technologies. As I said earlier, for example, the GPS, as I discussed, we need clock synchronizations or the 4 or the 5 clock which were there in each of the satellites. So we have to do better clock synchronization. When can we do better clock synchronization? Means when we have more and more precise clock. So I will discuss little bit more in details later, but I just wanted to tell that these are the technologies which people are looking, different domains of quantum technologies where people are looking in terms of communications and secure transactions and quantum computing. And I didn't touch the areas of quantum materials because that's not my expertise and I have little say on that. But like, so we will, I will summarize what I said. Like, we have 4 quantum technology pillar, which is what I just summarized. Like we have but it all grows from the basic sciences. One is communication, one is computation, one is simulation, and another one is sensing and metrologies. In all these things, what we are trying to develop is that we are trying to studies or understand the basic sciences, which is driven these technologies. And on top of that, we have to develop the engineering and control system, which is one of the challenges, engineering challenge we have, especially in the countries like India. We have very little development on this engineering and control system. And as you can see, there are many grad physicists which are good in theory and understanding of the physics, but when it comes to implementation in the lab, we are kind of little backward to the other countries. So we have to develop these technology skills also, and how to control and how we can develop these technologies control software system is education and training. So we have to build a new generations of the students which can do, or people which can follow up in this field. So I just wanted to because today is the discussion regarding the International Year of Science and Technologies. I just wanted to tell how this quantum technologies development is boom up. Like around 2018, there was lots of funding. Like India at that time wasn't started, like at that the countries like UK, US, and China at that time, European Union also the government put lots of monies in the exploration of quantum technologies. So that is how this research or exploration in this field has started, because they knows like what can we gain by doing or by putting money in this domain. So as you know that if somebody working in quantum optics, Peter Knight from Imperial College London, he was the one who was advisor in the UK at the time, and they are the one who put money in this quantum technologies for the first time in all over the world. After they put the money, then the US and other European Union also follows. So now, after like it started in 2018 in other countries, like India government started this national quantum mission, and by the end of 2024, or like say early 2025, they started the money. The mission has started, money started it to flow in the research lab. It haven't reached to us yet, but they have sanctioned the money. It will be coming soon. So we are just starting here in India. And I just wanted to give you some example of the quantum computing hardware. So as I discussed earlier, the picture which I'm showing here is a chip. Okay, a two-dimensional surface trap where we can trap. You can see those in this surface. I don't know my cursor is visible to you all or not, but those you can see the golden colors are the wires which carry the electrical. It can connect the voltage between the electrodes and the surface. And those golden lines which are flowing into the surface of the chips are the electrodes which will control the ions trap on these potentials. There will be a potentials, a harmonic kind of potentials generated between the center of the chip, and we will apply different potentials to implement the gate and the algorithms in the system. This is how we will implement quantum computing hardware in this system. So another example is that this is what people are exploring now. So we have developed three-dimensional ion trap. As you can see, when I say three-dimensional, the electrodes are spinning around the three-dimensional XYZ structures, and the bubbles, the dot here is in the center of this electrode. The gray colors are the electrodes. The red color and the blue colors are the laser lights where we used to trap the ions. Ions are sitting in the intersection of these electrode potentials and the laser lights. And this is an expanded views of the ions. And you can see that ions are confined in these three-dimensional potentials. And each ion will act as a qubit. Like we will see later also, each atom will act as a qubit, and we will implement the gates on them. We will do the gate operations and implement our algorithms. Similarly, here is a cartoon picture of this atom in the neutral atom in the lattice. The lattice are created by the superposition or cross intersections of the laser, and in the nodes or antinodes of the laser superpositions, you will the atoms will sit. This is how we will mimic the ion atom in a lattice. Okay. Or another people or group of the scientists who are exploring quantum dots as a superconductor, is a qubit for quantum computing. And another groups of the people, chunks of the people using photonics qubit. And photonic qubit is a good field of research for quantum communication, because they are the one who will carry the informations from the let's say a processor to the end user. To you, if you want to send an information from a bank to the end user as their secure OTP, then a photon is the one which will carry the information. So there are lots of research as a quantum computing qubit as well as this quantum informations carrier. Okay, so I just wanted to let's say discuss a little bit about the quantum communications. So in the quantum communication, as we said, that we have to explore the properties of the quantum mechanics to transfer our informations so that hackers or any other person cannot get the access to the information. It will secure our communications. But what we have to do is that we have to use our existing system like fiber optics cables or electromagnetic wave. This is how we are going to transmit the wave. As you can see the picture here, I send a pump light into a non-linear crystals, and you can see the blue light generate two daughter red color photon. So their energy, like they can produce entangle. What I'm showing here is that when I shine a laser light in a non-linear crystals, they can produce entangled photon pair. There's two red photon coming out from these crystals are entangled photon pair. When we do the second harmonic generations of destroying a photon and creating two photon, by the process itself, this is a way of generating, an easy way of generating entangled photon pair in the lab. So once you have the entangled photon pair, we will use this pair to transmit the informations. So when you read, what will this help us that I can read my states in one of the states and another states can be transferred. Like, because it's entangled, it will carry the same informations. And I don't need to worry about what is the other. When I have read the other one, I can know the informations of the other also. So it is a very interesting and important properties of the quantum mechanics, which we are going to use in this communication process. And this quantum information, the other challenges you will see in this quantum information is that since it is quantum, I have to transmit my information in a single photon, right? You need only one photon to carry the information, contrary to what we were seeing in our classical classical communications. Like when you speak in telephone, the sound wave what you are producing is converted into an electronic input, and it's a laser pulse of the laser light is transmitted into the fiber. Okay, so in the classical, like if you open the classical communication channel, any of the old phone receiver, or you will see that there is a laser source. So the laser source will emit pulse of the light according to our frequencies which is controlled by an electronic signals, right? So the pulse of the light will carry millions of photons. Okay, this is how our information transfer is happening now. When we are speaking in the phone, it's a pulse of the light going on according to the frequency and the amplitude, and that it varies. Okay, but in the quantum, we have to transfer single photon. What does it mean? The photon information can be lost, right? It's a single photon. It can, while it's propagating, it as the loss rate is very high. But there is one interesting properties of the photon, that it doesn't talk to the it's neither like it doesn't interact to its surrounding very well. So it's a good point or bonus point of this photon. That's why we can use the photon to transfer the information. And generally, when we said entangled photon, we generally think of the entanglement in terms of polarization degree of the photon, because for the detections and the preparations of the light in that polarization degree of the photon is easier implementation point of view. This is from the engineering aspect of this, when we look the engineering aspect of this kind of technologies. So we wanted to explore polarization's degree of the freedom entanglement to transfer the informations. And the challenge what we see, as I discussed earlier, is a weak signal is only one photon carrying, and the detection generation is a issue. This is a big research field people are exploring now, and they are trying to develop. Um, for example, like single photon generation, how like earlier people used to do is that people just reduce the intensity of the light by using hundreds of neutral density filter and try to reduce the intensity and get one photon. But that is not very convenient way, and also the efficiency is very low in that. So we are trying to develop a single photon source which you can control anytime, send the information, like the control and the handling is easier. But what are the advantages? This is very challenging. As I discussed, it looks very challenging to us, right? So, but it has lots of advantages, right? Quantum cryptography and cyber securities. What I have discussed is there in the right side of the example, right? You have an input electronic signal. There is a source of driver, and the LED is there or laser is there. It emit pulse of the photons, and that will come to a detector, which is a photo detector. And once it detect, we need an amplifier to amplify the signal, and we hear or we get the output. So the photo detectors here we are going to use is a single photon detector. It is a quantum, if it is a quantum technology, they are kind of a valence photodiode or single photon detectors. Okay, so what are the research we are doing? People are driving. You can see in this nowadays literatures, they will be keep on talking about the material. Scientists will keep on talking about developments of the materials which can do single photon detection with high efficiency. So there are many diverse areas of the research happening in this communication, quantum communication family also. And another thing which we are going to use if for quantum mechanics is the no cloning theorem, which I said, right? We like the detection, once we detect glass and we cannot have, we lose the informations what we carried. So what we were doing presently in this communication process, people are trying to develop is that quantum cryptography with new encryption by developing the single photon source and the detection efficiency. So the left side is I tell how we generate the entangled photon pair. Right side pictures I just show the ways of transferring an information in the classical channel, and we are trying to develop on this. So the quantum technologies doesn't come by itself. What does it means? It borrows the informations from the classical technologies, and we build up the instruments, we develop the technologies. We will still may use some of the existing technologies and try to build up or replace with the quantum technologies wherever it is there, which is possible to us. If someone has any questions, please write to me, or you can stop me anytime. I'm happy to answer. Okay, so one example among the four particles, I just wanted to give another example is a quantum sensor. Okay, so a good example of the quantum sensor is atomic clock. The right-hand side picture is the cesium fountain clock from the National Physical Laboratory, London. This is part of the where the atomic fountain is there. So it's a jargon, I think, for the people. So where what happened there is that there are cold atoms which you can lift off to the to a height and it will fall down. And during the process, we will interrogate and get the measure the frequency of the ground state of the atoms, and that's how we map to the frequency of the that's how we map to the unit of the second, SI unit of the second. So we are still using present definition, or while we say the definition of the 1 second, we are still using the ground state splitting of the cesium, which is in the gigahertz. So the accuracies of our second is nanosecond, nano to 10 to the power the minus 15 second, but in the laboratory. But in the satellite, we can get 10 to the power minus 12 is what we generally achieve in the those clocks carried in the satellites. So what I'm showing here is some histories of the clock, right? Earlier, people used the sun as a clock, right? So the sunrise, sunset, change of the winter tells you that when we have to, like when winter is coming, what are the crops we have to plant in the fields or in the vegetables. This is how people use. It evolved with time, becomes, we have seen the pendulum clock, after that the quartz clock. The quartz clock is the one which we use in everywhere in houses. All the wall clocks and all the rituals generally is based on this quartz clock. And after that, we use the present definitions of the unit of the second is used is cesium ground state, which is a cool cesium trap in a magneto-optic trap, and do the interrogations. Okay. So now a little bit more in the scientific aspect of this quantum computing. So in quantum computing, what do we need? In the classical computing, we know that we implement all the gates, all the algorithms using bits, right? The bits are 0 and 1. So in the quantum, it will be replaced by the qubit, which is a superposition, which can be a system of two state, which replace the classical bit 0 and 1. So if you think of representing or try to understand, it can be represented in the block sphere. The top state is the 0 and the bottom state is the 1. It can be used because it has two states, 0 and 1. This can be used to represent or to understand the science or the physics. We can think of in representation in the block sphere. As I discussed earlier, ion trap in the and harmonic potentials can act as a qubit. But how it will act as a qubit, we will use the ground state and the excited state of a particular transitions. We will choose the transitions according to our requirements, and there are many properties we have to see in these transitions that I will explain in the later slides. So we will implement the qubit using this kind of transitions. And what do we look in the quantum computing? Once we have a initial state, we prepare a states, and what we have to do is that it can represent the information of the states. So we have an initial states, and what we will do is that we will implement the algorithms, or this is how, right, initial states, algorithm implementations, we will get the final answer. So these implementations of the algorithm or the gates are done using a unitary transformations. They are called universal quantum gates. They are a family of the unitary transformations. We have to use unitary transformations to start from an initial stage to a final stage. And I will give some example how we experimentally implement in the lab also. And then this is like this, again, we keep on emphasis on the initial states, because the initial state preparation is very important. Being a quantum phenomena, nobody can prepare a state to 100% efficiency. But people prepare 99.99 fidelity states experimentally. Okay, and once we do that, once we prepare the initial states, we do perform the universal families of the unitary transformations, which require or dictate by our algorithm, and then we will measure the output. states by projection measurements. Okay, projection. So what we are looking for, like if let's say I have to choose a quantum system. Either it can be ion trap, it can be a superconducting qubit, quantum dots. What are you looking at in the system? What is the most important thing if you want to implement as a quantum computer? The most important thing or the key merit which we are looking is the quantum noise. What is the quantum? Generally, it's called decoherence in the language of atomic physicists, or I think decoherence. It has related to the decoherence. Okay, so what does it means that this uh, when I prepare a state, the state will remember its information of the initial state as long as it retains or it remember who am I or from where I started, who is my neighbors, how I am look like, all those things. This is called coherence. Once it start losing these informations, they started losing decoherent, become decoherent. So what is the longest possible quantum computer or quantum algorithm which we can implement in the lab is given by the coherent time of the system you choose. I think the spelling is wrong. The coherent time of the system you choose divided by the time of performing unitary operations. Because I have to implement an algorithm, I have to implement for this algorithm how many unitary transformation or operations I have to apply. Right? Depending on that, like if I have to apply 100 unitary operation, then my coherence time of the system should be longer than that. Let's say one unitary operation take 1 second, then I should have like a system which coherent time is longer than hundreds of seconds. That's what we will look at, and that's how we will decide what quantum system or what particular element we can use as a quantum computer. And these are examples of some of the qubits which we will be using and which I will be using. So this Hadamard gate, like I will explain, these are the gates we use. It's Hadamard, Pauli, and the 2-qubit gates control it. These gates, like Hadamard, Pauli X, Pauli Y, Pauli G, phase, and this control gates, they call the combining the single qubit gates, which is on the left side, and the 2-qubit gates, which is on the right side, combining these two form a universal set of quantum gates. If our system can perform this universal sets of quantum gates, then it can act as a quantum computer. We can use it as a quantum computer. Because we need 2-qubit gates to generate entanglement. Entanglement generations cannot be happen with a single qubit gates. That is why we need 2-qubit gates. So any system, any computing system which we pick should able to do this entanglement generations, which are generally done with the 2-qubit gates, and the state preparation, state manipulations generally done with the single qubit gates. And okay, so once I have prepared my states, I implement the algorithm. So what I'm going to do, how I'm going to measure my informations, how I'm going to read out the properties of that. So this we will use, I want to emphasize again, here we will use classical methods, existing classical channel to read out the quantum information. We don't have any quantum channel to read out quantum information. Okay, so what we are going to exploit is that we are going to exploit possible classical channel to interact with the quantum system the most. Like the interaction has to be very large. We wanted to improve the efficiency. We should have larger interactions. So for a good we as I discussed earlier, we are going to do projective measurements. Coupling of the qubit with the classical system should be very high. And when we set a good quantum algorithm, the end of the day, we will be giving a superposition states. Okay. From a superposition states, we are going to measure a particular states, right? When we measure a particular state, because of quantum measurements, the states is a superposition state, you will be allowed to measure only one state. You cannot measure oh, this is not the correct one, I should go back and do the measurement. No, you cannot do that. The information is already lost once you measure it. So we have to judiciously choose which state we should measure, which will give highest information of the system. right? Whatever, even though we are allowed to do parallel computing, we are allowed to do parallel computing, we cannot read all the states. We are allowed to read only one state from the intent superposition state. So we have to choose judiciously what is the state we will read to get maximum information out of the system. And generally, when we do projective measurements, we think of strong measurements, right? But the strong measurements has difficulty to implement, and it has readout also difficulty. So what people do is that we do weak measurements. Scientific communities or people do weak measurements, and it perform continuously, and we average out the results. This is how, why whenever you read any quantum computing, quantum papers, they keep on saying about fidelities, measurements, error, or the probability, because it's a probabilistic phenomena, quantum phenomena. Reading only once will not give all the informations. We have to read multiple times. So sometimes weak measurements, we generally implement weak measurements to do this quantum readout. For example, I can give an example like uh, let's take the right side example. The two black vertical horizontal lines are the levels, are energy levels of an atoms or the state, 0 and the 1. So initially, the blue dot represents the atoms is in the ground state, red dot represents the atom is in the excited states. Okay, I can prepare the states in any of the superpositions, but when I detect the emitted photon using a photomultiplier tube. When I detect a photon, I know that my atom is just before detection, it was in the excited state. If I don't detect a photon, then it is in the ground states. What did I use? I use a laser light to excite the atoms from the ground state to the excited state. This is an example of the classical channel. And I still use PMT or a valence DC or photomultiplier tube or a valence photodetector. These are all classical instruments. I just read quantum character or quantum informations or quantum physics using classical channels. This is what I am showing. We have two amplifier and we read out in oscilloscope. So whatever our readout are, we are still using classical instruments, classical channels, classical method. So what we will look is that for doing a good implementation of good quantum computing, we should look high signal to noise ratios for our signals. So it means the coherence time has to be longer, or coherence time has to be longer, decoherence has to be small. Okay. With this, I would like to tell you, like, now as I am an experimentalist which work with laser cooling of atoms and ions, trapping of atoms and ions, I wanted to say that my field has some advantage than others, or why I'm interested in exploring this kind of particular fields, or what are the benefit we will get from studying this kind of particular fields. As we say that good technologies are the technologies which everyone use, and it has to be operable everywhere. So in this kind of experiments, we will use atoms and ions. Atoms and ions are universally the same, right? They are universal properties. Their mass, the resonance frequency, the matching laser which can tune, they are all exactly the same. So the technologies which develop using this kind of properties is a very good example of the quantum good technologies. And on top of that, there are well-developed techniques, how to prepare the sample, how to isolate my system, how can I individually control and detect qubits. All these things are very well developed in this kind of communities. As you can see, there are many Nobel Prizes for single photon detections in the Sir Harauche and David Wineland, and the manipulations of the single photon with optical tweezer in Atharaskin. Like many people got Nobel Prizes in this field. So it means that these state preparations, detections, control systems are well developed. As you can see that the string of the dots here in the bottom of the pages are the ions trapped in a linear Paul trap, where we can implement the quantum qubits. And individual atoms or ion act as a qubit, and we have to do the control gate operations and the individuals ions which is trapped here. Okay, how I am going to do individual controls? Just okay, mainly I don't know, the students will learn from here. So what I'm drawing here is that I have a two-level system, ground state 2 represented, excited state represented by 1, and which has a separation, energy separation proportional to this omega 1 to the difference between the frequency. I assign another laser light which has an intense electric field ET and frequency omega. That's I can tune the parameter of my laser light, because I am the one who is sending this light. I can control my lasers. So I can control my detuning. But when my lasers and interact with the atoms, atom has a lifetime in the excited state. For example, for P 3 by 2, that is S to P transitions of the rubidium, the lifetime in the excited state is of the order of nanoseconds, right? And the detuning is the difference in the frequency between the my laser and the frequency of this energy separation between these two levels. Here, one very important concept is that I'm defining is omega R. Okay, omega R means the Rabi frequency. What means it is the interaction strength between my laser light and the properties of the atoms. So this amplitude E times E naught by H come from my intensity of the light or the laser I use. And this dipole matrix elements between the ground state and the excited states come from the properties of the atoms. So this is the interaction light and interactions with the atoms. Light atom interactions give me the strength of the interactions, give me the Rabi oscillations. Okay, if I plot these oscillations, then this Rabi oscillations, we can extract it from the by calculating this susceptibility. The susceptibility has two parts. One is the imaginary part and the real part. So if I solve this expression for these two-level interactions with the laser light, I can extract the susceptibility and the real part proportional to the dispersion and imaginary part proportional to the absorption, which is represented by the blue curve here in this. Why am I there? But instead of sending a light which is detuned from the resonant, I send a light which is exactly on resonance. Means my omega is exactly equal to omega 1, 2. Okay. Then what will happen is that the atoms will oscillate between the ground state to the excited state. Here I am plotting tau. This is the time, and the x-axis is the y-axis is the probabilities of finding the atoms in the excited states. Okay, as you can see, the atoms is oscillating between the ground state and the excited states, and the period of this oscillation is proportional to the strength of their interactions, omega r. So omega r, larger the omega r, I can oscillate faster. So the interaction strength give me this oscillation. Okay, now here we will see you can see that, right? If I sign my lights for a particular time, let's say slightly less than 2 tau, 2 microsecond, my atoms will go from the ground state to the excited state. It flips. I prepare my state in the ground state, and I wanted to flip to the excited state, which is called X gate. In those example, I have given the single qubit gate. This is an example of the single qubit X gate, which will flip my population from one state to the other states and vice versa. And there is a time where I mark it pi by 2 if I, at this particular transition, at this particular point of time, there is equal superposition, because there is it's a 0.5, right? Equal superposition of the excited state in the ground state. This gate is called Hadamard gate. Okay, gate is called Hadamard gate. And if I add my Hadamard gate in the ground state, then I can make in the superposition of the ground state. So what does it means? I just need to turn on my laser light for this particular time, let's say 1 microsecond. Then I will make my atoms in the superposition. If I start with the ground state or excited state 1 or 0, if whenever I shine, my pulse of the light turn on, my pulse of this light for a particular path and time tau is equal to 1 microsecond here in this picture, then I prepare my state in a superposition states. This is how we implement the gates. There are a few examples. I'm giving single qubit gates in the experiment. This is how we prepare the gates in the lab. Okay, there is another important concept of light atom interactions which we will be exploring is the Doppler cooling. As the name suggests, Doppler, we exploit the velocity and the proportionality to the energy. So because of the development of this Doppler cooling, these three gentlemen got the Nobel Prize in 1997 for development of the demonstrations of this Doppler cooling in the laser cooling and the trapping technique, right? Steps to Cohen-Tanuzzi and Bill Phillips. So the basic idea is that here is we have an atom. Let's say I am an atom and a counter propagating and laser light comes and hit me. Since if I was traveling with a certain velocity v, then my velocity will be reduced. How it will be reduced is that because I will absorb a photon which frequency is lesser than the resonance frequency given by my velocities. Like the detuning is proportional to the Doppler effect, which is detuning is proportional to my velocities. But because of Doppler effect, I'll go to the excited state and come down to the ground state. When I come down to the ground state, it will scatter. It's a scatter photon. It's a probabilistic. It can scatter in all the possible directions. If we do a change in the momentum calculations from the beginning to the end of the calculations, we will see that the velocity is reduced by h bar k by m. To give you a perspective how much we reduce by one interaction, is there some one interactions, then one like for rubidium-87, one interaction like B required is of the order of 6 millimeter per second for rubidium-87 atoms. And the temperature limit, the minimum temperature which we can do by doing Doppler cooling is 146 microkelvin. Okay, so this is the magneto-optic trap. So if we wanted to go to Bose-Einstein condensation, this microkelvin should reduce to nanokelvin. There are different processes to do that. This is the starting point of demonstrating Bose-Einstein condensation. Yeah. And in the later part of the other physics I wanted to tell you is that AC Stark-Ship. When a detuned laser light interact with level energy level diagram or a two-level system or any other atoms, there will be the level can be shifted, which is given by the Stark-Ship of the level. It depends on the intensity and the detuning of the lights. I don't know how much time I have.
Yeah, you can continue.
Okay, thank you. Okay, so with this example, I come to here that I wanted to give you some measurements, some experiments we did in a quantum sensor. So one example is there's optical atomic clock, where I was doing during my postdoc. One of my experiment is related to the atomic optical clock. I wanted to tell a little bit more on that, my experience. So what we have to do is that when we said atomic clock, there are many things like the laser which we use to interrogate the atom is very important. It's very, very important. The energy transitions we choose for a particular atom is also very important. So for example, the atoms I work is the lutetium, and the lifetime of that clock transition is excited state lifetime is thousands of years. If you remember for rubidium in the few slides before, I told you that the lifetime of the rubidium excited state is 26 nanosecond. Okay, so this 26 nanosecond, if you compare this nanosecond with the thousands of years, these are the clock transition we choose. So when we choose the clock transitions, the lifetime of the excited state has to be very, very large. Okay, this is what I wanted to explain here. So in order to interrogate that lifetime, we have to make a laser which frequency is very low, of the order of millihertz. So what we do is that once we have a laser, okay, what we will do is that we will lock the laser into a cavity. Okay, that laser cavity, which I am drawing here, laser cavity has a drift of microsecond. This cavity is actually a cryo-cool cavity, and which frequency or is of the order of millihertz. Okay, once we lock the laser into a ultra low expansion cavity or a single crystal silicon cavity in a cryogenic chamber, then we will interrogate with the atomic transitions. But this laser has to be stabilized for the long-term drift and the short-term drift. How we did is that the laser frequency, if you remember, is of this nanometer, right? It is of the 10 to the power 14 hertz, terahertz, the laser frequency. And since this is very high, we don't have well-developed technologies to read out this frequency. So what do we have? We have telecom frequency readout, right? Which are in the megahertz or gigahertz. Our Wi-Fi is in the gigahertz. So we have the information to read out gigahertz frequency, but we don't have good information to read out terahertz frequency. So we have to down convert the terahertz frequency to megahertz or gigahertz frequency, which is done with this frequency code. Okay, this frequency com is a device which will down convert the frequency from the terahertz to the megahertz. It's a very expensive instrument. In India, 1 or 2 lab has this. It's like almost 3 or 4 crore, and it's this now a price of this frequency com. And once you have this frequency com, it has to log to a long-term drip maintenance called hydrogen maser. Okay, so this hydrogen maser is synchronized with SI calibration, System of International Time Calibration, which was done with this International Bureau, or I can say the example is that our internet is all synchronized with SI. So once your computer is connected to the internet, the time will be like your computer time, even though it was slow earlier, it will be synchronized automatically. This is how we do the measurements. We have a laser, but it has to be compared internationally through this GPS time-based system of international calibrations. What are some advantages for atom? What we have here in the atomic clock is a perfect oscillator that we all know. With a single ion in a trap, we can measure a height change of 1 centimeter, which is proportional to the 10 to the power minus 18 fractional frequency stabilities. Our GPS got 10 to the power minus 12 now, whatever stability we have, but this single atom atomic clock we have 10 to the power minus 18 stabilities. So what I would do in this measurement, what we were trying to do is the magic wavelength measurements. What is the magic wavelength measurements? As I think in Professor Nimai also mentioned magic. It is something very peculiar. What in a particular, we can measure the clock frequency, but we wanted to measure this magic frequency and exploiting the Stark induced AC Stark shift. And this is the formula. I don't want to go through the details of the formula. This is the formula we are going to use for these measurements. But you can see here in the plot. In the left side of the plot, there are two plot, right? One is theoretical plot and one is the dotted plot, which is the theoretical plot, but using experimental parameter. BIS is the low-level experimental parameter. I'm talking about this is for a particular element called barium. So you can see these two curves intersect somewhere at a particular after 0.063 around here, it intersects. So these two measurements is related to the one of the systematic of the atomic clock frequency measurement, or let's say frequency measurements of atomic clock. We cannot predict accurately because there is a separation. There is a separation between the dotted plot and the solid plots. We have to pinpoint this data by measuring this zero crossing. Okay, this zero crossing is, what is this zero crossing? Is the Stark shift goes to zero at that particular wavelength. So if I shine my light at this particular wavelength, my atomic clock frequency will not change at all. These are the wavelengths where people used to trap their atoms in the optical lattice also, because the Stark shift induced by the optical lattice is zero, so they can manipulate the properties without worrying about the systematic effect using the Stark shift. It's an error. Let's say it's an error. They don't need to worry about the error. So what we have to do is that we have to measure this zero crossing frequency in the atomic clock transitions. How we going to measure is that, as I told earlier, when we shine a light, the Stark shift, if you calculate the Stark shift for a multi-level system, is given by this expression. The first term is the DC Stark shift, second term is the XC Stark shift, and you will see something very interesting here. Here is a term which is proportional to this 3 cos square minus 1. Because this is a combination of two terms, we can make it zero by equating this theta equal to like somewhere called 53.3 degree. We can make this term zero. This is how we are going to cancel the Stark shift. This is how people find a magic wavelength in all the atomic transitions. Okay. And then, as I said earlier, I am going to do these measurements for barium. And the barium has this, like, I don't think you don't need to worry about this lasers. There are many lasers to use and trap. So what is important is that I have to shine an external light 653 nanometers and do the measurements. When I do these measurements, we are going to quantify a systematic shift called blackbody radiation, which is proportional to temperature. I'm not going to tell details about this experiment. Somebody interested, we can talk later, or details can be found in the papers I have mentioned here. So I just wanted to do how we do quantum measure. I just wanted to show you how we do quantum measurements in the lab. So we trap an individual ions in our ion trap. This is the example of a quantum system, which is confined in an ultra-high vacuum chamber, separated from all the external environment and confined in a harmonic potentials. Okay, many details about experiment. This is how it looked like. The picture, if you can see on the left side top picture, the single ion is inside these trap potentials. You can see in the window, there is a viewport where you can see there is a little pink color spot inside. This is where we trap the ions. And on the bottom picture is the accessories like where all the lasers come and all the accessories of the experiments. A complicated setup, but it's not that complicated for an experiment, but theory may look complicated, but it's the way to generate different lasers, different frequency, different detuning, control, fiber couple, all these things. We don't need to worry, but I just have to send a laser light, which is at the 650 nanometers. When I do these measurements, I have to check the projection noise of my measurements, which will tell me that my measurement is quantum or not. Because we do projection measurements, we should always check the projection noise of the system. That will tell my measurement is quantum, because I can measure 1.5 hertz projection noise, and this is corresponding to my measurement setup. So what does it mean? It means I can measure 1.5 hertz accurate frequency. Okay. This is my capabilities of this experimental setup we can do. And once I found out my projection noise and confirm that, then we do the frequency measurements. And on top of that, when we do data analysis also, there are tricks we have to implement. Okay, so I measure, there are two terms I explain in the Stark shift. One is the scalar shift and one is the tensor shift. So these two terms, if is proportional to electric field E square, if you see the expression on the right side, they all proportionals to the E square. So if I take the ratio of these two, I can cancel the intensity noise, right? Because the E and E cancel, so my intensity noise is common, so I can cancel it out. So, but as I discussed earlier, I have to measure this theta, which is the magic angle, and this frequency. But if I measure both of them and do the ratio, take the ratio of the measurements, then I can cancel the noise of this intensity and I can get more accurate crossing of zero crossing. This is how we did, right? So uh, this data, one is the scalar and one is the ratio. As you can see, when I do the measurement with the scalar, I can get this my measurements accuracy to 459.2. This is in the terahertz, or you can see in the wavelength 652.9. This is my accuracy of the measurements. But if I take the ratio, I can increase my accuracies by 1,000 times, 10 to the power 3 times, where I can get the frequency goes to this 10 to the power minus 6 meter micron. I can get this accuracy in the micron, and I can similarly, I can increase the frequency to 1,000 times in the terahertz also. So we not only needs to do quantum measurements, we have to implement judiciously ways of doing the measurements. This is how we did the experiments. With this, I would like to conclude my presentations. So we go through, I think we started with what are the different domains of quantum technologies and what we can do. And then I have shown you one example of doing magic wavelength measurements, which is a quantum measurements using a single trap ions. When we do these measurements, we use single photon detectors or we use camera. Generally, all these measurements are done with single photon detectors. So its measurement has to be confirmed whether it's a quantum measurements, and then we have to do judicious or wise analysis of the data to get more better accurate result for this. But what I want to say is that whatever the measurement we did, we use classical channels to read out the quantum informations. With this, I would like to thank all. I joined Kanpur in just 2 years back, and this is my lab just starting. So because I haven't, I don't know, I just wanted to show what is the present state of the IIT Kanpur. We got some funding from the different funding agencies, as I discussed in the previous slides. We are going to build the lab soon. We're trying to build up the lab. With this, I would like to thank you all. Any questions?
Thank you, Dr. Ranjita. Now we can have some question and answer session.